Today I'll be talking about AI on the frontier, which is currently ranked #1 on the top 500 list of supercomputers worldwide. The overall intention of this talk is, not only to get into just like the absurd specifications, capabilities, and some of the work that takes place on frontier and at Oak Ridge National Laboratory and otherwise within the DOE system in the national labs, but the kind of key takeaway that I'm going to try to communicate here is basically, I'm not that smart, I'm not that special. If they let me on this thing, there's a lot of opportunity for some of the people in this room and elsewhere to take advantage of this incredible system for your own projects or your own work. A little bit of a background here. The Department of Energy and the national labs have been building incredible supercompute systems for decades. However, they encountered a particular barrier. They couldn't reach exaflop level compute power with the current systems and architectures. So the DOE allocated roughly $2 billion to try to solve this challenge. And exaflop, it starts to get into these like weird units you've never heard of before. So what does that mean? That is 1 quintillion floating point operations per second in double precision. So FP64, which is even more challenging than a lot of the precision levels that we see in AI. So that's 1 followed by 18 zeros. So this is the current list of top 500 supercomputers worldwide. You'll notice there's 2 DOE systems right there at the top. These were the first 2 systems that were a result of this DOE Exascale project. They're working on a third, and actually, so there's my friend Frontier right at the top, #1. The second system, Aurora, is actually only a few miles away from here. It's at Argonne National Lab, which is in a kind of a western suburb. Little inside intel. I got lucky here because they're still kind of tuning and dialing in Aurora, and Aurora will likely overtake Frontier in terms of raw performance when the next list comes out in November. But what you'll notice is both of the DOE systems are twice as fast as the next system, which is at Microsoft. And then, these poor guys in Japan and, in Finland there at the bottom are kind of on a different level. So what is Frontier? Certainly anybody can read this. I want to be respectful of time. David runs a tight ship. So it, blah, 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 74 Olympus rack HPE cabinets. You'll see those later, and I'll break out some of the compute specifications. That's the system. In this case, they have the rack cabinet doors removed. There's a lot of really interesting things. So when you step in the room, probably 3 things really jump out at you. #1, it's kind of warm, which, okay. And then #2, it's dead silent, which is really interesting. And so you can see the blue and red loops there. It was also one of the first systems to use warm water cooling, even as opposed to chilled water. And there are massive evaporators on the roof, whatever else. But needless to say, the lack of fans and air cooling contributes to how quiet it is. And the third thing is, it is spotless. Speaking of running a tight ship, I mean, this is not some like PR photo where they kind of stage anything. It is really that clean. So key specifications here, approximately across the entire machine, 579,000 and change AMD EPYC cores, 4,524 terabytes of RAM, 700 petabytes of storage, which, okay. But the most impressive thing about the storage, it has a combined performance of 15 billion input-output operations per second. 72,384 AMD MI250 GPUs. That's the most important thing to me in my work. Uses, depending on what it's doing, whatever else, 20 to 30 megawatts of power on any given day. Warm water cooled, touched on that. Given the work that takes place at DOE, some of the budget stuff isn't exactly clear. But it's basically roughly $600 million construction cost out of that $2 billion that was allocated across the 3 machines. Another kind of interesting one that, when you talk to the guys at Oak Ridge who are just like absolutely incredible, they let me know that the power bill from the Tennessee Valley Authority that powers the machine is roughly $50 million a year. So that's my team. It's a cool picture, and it's not a deep fake because I'm even wearing the exact same outfit. And I present this to not only kind of give credit to the incredible team that we have, but also kind of go through some of these characters. So on the far left, that's my co-founder and CEO, Trey Lauderdale of Atomic Canyon, me. That's Richard Clafter, our chief AI developer. And then on the right, in the hoodie, is Dr. Thomas Evans. He heads up high-performance compute applications for nuclear at Oak Ridge. So how did I end up in this? And also, how might you end up in this? So my co-founder, Trey Lauderdale, that was on the far left, a couple of years ago, he moved to San Luis Obispo, California. And if you're not familiar with San Luis Obispo, California, it is home to the last operating nuclear power plant in the state of California. It's like roughly 2 1,100 megawatt reactors that provides something along the lines of 10% of the power for the state of California. So he moves there, and he's got a tech background, tech guy, just roaming around town, coaching his kids' soccer games, stuff like that. And Diablo Canyon Power Plant is the second largest employer in the county. So he's just bumping into all these people that work in nuclear energy and nuclear power. And you can kind of imagine how the conversation would start to go, right? Like, oh, what do you do? I'm a tech guy. Oh, what do you do? I work at the power plant. And Trey would kind of ask some of the same questions, and there was always the same response. He'd say something like, wow, you guys are splitting atoms over there, generating all of this power. This is so incredible. I bet you have really good internal IT systems and technology. And they would laugh hysterically every single time, like, oh, no. It can get a little, I would say legacy, given the safety and criticality to life. Well, criticality, probably shouldn't say that, but just the nature of the application. So he actually lives 12.8 miles away from the main gate of Diablo Canyon Power Plant. That's Diablo on the left there. Nuclear power. What does any of this have to do with anything, and kind of how do we end up here? So what we ended up discovering is that due to regulatory requirements, INPO rating scores, these things get ranked. There's the Institute of Nuclear Power Operators. Diablo Canyon is level 1, which is the highest ranking. And especially after visiting, you start to realize that their policy, process, procedure, and documentation is you can't comprehend it. It makes something like Frontier look moderate. I'm talking policy, procedure, and documentation to change the trash bags in the entire facility. So over the span of the roughly 40 years that Diablo Canyon has been online, they've amassed billions of pages of documentation. So they have dozens of people whose full-time job, 24/7, 365, is to work and interact with this information and find these resources for other people on the team. There's, at any given point in time, 1,200 people working at the power plant. So they support that. And you end up running into cost challenges, regulatory compliance challenges. They have on-site Nuclear Regulatory Commission inspectors, and you can actually be fined. Well, you can be fined for a lot of things, but one of them is not having access to information in a timely manner to be able to respond to interactions with the Nuclear Regulatory Commission. Then you start looking through this data and you realize, I maybe understood some of the words in the first sentence, but after that, I'm completely lost. And we found that any of the currently available AI models in benchmarking have no clue what some of this really obscure language, jargon, acronyms is. And that leads to incredibly poor performance. So as we looked at deploying AI in this field, we realized, wow, we're going to really have to do some foundational model work to make this application really work. So Founded Atomic Canyon. Step one, we found the Nuclear Regulatory Commission Atoms database, publicly available, work of the federal government, no copyright issues, whatever else. So over the span of some time, we downloaded and indexed approximately 53 million pages of this publicly available documents from the Nuclear Regulatory Commission. We developed a full ingest pipeline to handle these documents, including optical character recognition, layout understanding, tables, segmentation, et cetera, and used that to develop our foundational AI training data set. Step one was essentially taking AI to nuclear school. We had to train all of our foundational models on this data set that we developed to understand, how zirconium alloy interacts with corrosion in, the control rods of a nuclear reactor. We're going to then take these, sentence embedding models particularly, and integrate them with search application that's going to use not only vector search, both dense and sparse, but also more traditional approaches like BM25, bag of words, conditional fields, those kinds of things. And then we're going to take that and use that information to feed generative AI applications as well. So you kind of look at it and you think, well, you're essentially like Googleifying these billions of pages of documents, and then using that incredible search and recall performance to drive and feed generative AI applications with actual relevant information for not only higher quality output responses, but to address typical challenges like hallucination and so on, which, needless to say, in the context of nuclear power, would be very problematic. So our first project on Frontier is called Fermi. Another great little Chicago connection here. So Enrico Fermi, if you're unaware, was a nuclear physicist that essentially did the first self-sustaining nuclear chain reaction. And it actually happened, another great Chicago connection, basically down the street. It was underneath the squash courts at the University of Chicago. We, first things first, developed a valuation framework, not only important for any AI application, but particularly in nuclear. If you look at the sort of genesis of this project and these billions of pages of documentation and all this different stuff, the culture is such a strong safety culture. Probably one of the main standouts of when I visit nuclear power plants is, it takes 45 minutes to get in there. There's all the security stuff. You're wearing a dosimeter and booties and all, whatever else. And it's kind of a special experience to walk downstairs and have a guy in body armor with a rifle behind you yell at you because you're not holding the handrail properly. You learn to kind of get it together really, really, really quickly. So if you look at that sort of safety culture and rigor, they have benchmarks, they have testing. Nobody just flies by the seat of their pants in nuclear. And applying artificial intelligence to nuclear, we can't either. So evaluation and benchmark first, always. So took the data set, used Llama 3 for some synthetic training data generation. We also have an incredible suite of advisors. If you don't have at least a half a dozen people around with PhDs in nuclear engineering or nuclear physics, there's no way we'd be able to do this. So validated that with them. And our current project is essentially taking an extended context length BERT-based model with some other features that we've extracted from other architectures and other implementations, all based on benchmarking, to do what is essentially a nuclear-aware tokenizer-based model with an extended context, and then using SPLADE version 2 sparse embeddings, which is kind of another interesting, unique approach as opposed to the more typical dense embeddings that you would see in AI applications. In terms of back to the benchmarking, what we currently see, and we're still running iterations and doing evaluation, et cetera, but we currently see a hit rate of 94% recall based off of actual user queries from end users who we also collaborate a lot with. Then you throw the nuclear, PhDs in, et cetera, and that's really where these numbers come from. Bringing Frontier back into this, so The last training job from yesterday was 22 node hours across 32 nodes, 22 hours in runtime across 32 nodes utilizing 256 of the AMD MI250 Instinct GPUs to a total of 704 node hours. I'm going to get into kind of what that means and how that relates to our application in the project here. But from the application stage, there's a variety of ways to get on these systems that I'm, again, going to go into more detail here shortly. But we were allocated 20,000 node hours. So you can start to see that our big final training job is 704 node hours. We have plenty of time left over to put Frontier to work. How? Like how did all this start? How did we go from where this began to I have my RSA secure ID token and can log into Frontier? I think another important thing to note is while we're working with the DOE and the NRC, et cetera, that's clearly energy stuff. Department of Energy, nuclear energy. Yeah, it makes perfect sense. But you start looking at Frontier and talking to some of the people at Oak Ridge, et cetera, and you find out very quickly, oh, Pratt & Whitney uses Frontier for simulating jet engines. GE uses Frontier for like an unbelievable array of things. There are a lot of projects running on these Department of Energy systems that have nothing to do with energy. So how do you do this? Step one, apply. These are all links. So we share these slides or whatever else. You can go check this stuff out. The easiest and fastest is what they call a director's discretion application. So the director of the individual national laboratory has essentially like a like a supercomputer slush fund, basically, where you just kind of work it up to the director, and there's a committee and a variety of other reviews and whatever else. And I'm thinking when we started talking to the Department of Energy, I'm like, oh my God, the federal government. This is going to take years. Like who knows what we're going to have to do to get this going? And it was literally one hour meeting and a 2-page Google Doc where we described what we were doing, who we are, how it applies to things, and they have like guidance and examples to kind of get you through this. And certainly specifically to us, they warned us from the get-go, this application has the word nuclear in it. So this application process is going to be delayed a little bit because there's actually which makes sense, there's a export control review process with the Departments of State and Commerce where they look at your application, kind of what it involves, et cetera, and they essentially make sure that you're not going to use DOE resources or generally kind of get yourself in trouble with the very stringent federal laws as opposed to internals of nuclear and potentially contributing to nuclear weapons proliferation, enabling things with some people that we don't think should have nuclear reactors, those kinds of things. So even with the review with State and Commerce, roughly a month later, FedEx envelope, Frontier fob, little interview, whatever else. Yes, I'm me. This is this, and read the documentation. On this laptop, wherever I run SSH Frontier, and I'm on the fastest supercomputer in the world. Speaking of which, get a nice little banner. Sometimes you get used to it, sometimes you don't. But you get the first sentence alone. This is a federal computer system and is the property of the United States government. You're like, okay, yeah, that's right. This isn't like my local Linux box or whatever. Like, I gotta get in the right frame of mind, right? So, what does the actual system look like? You log into this thing like, Linux command prompt. What do I do now? So, Frontier itself is built in conjunction with Hewlett-Packard Enterprise, who acquired Cray, who some people might remember that name. So Cray has a SUSE Linux variant that they use on these systems. Doesn't really matter much. The important thing is there are essentially modules of packages in conjunction with DOE, the lab, whatever else, where you can like load and unload these modules essentially. Because needless to say, you can't, you don't have sudo, you don't have root, you can't go install stuff all over the place. There's a job scheduler called Slurm. If you haven't done multi-node distributed computing, it originally came from Lawrence Livermore National Lab, and now there's a corporate entity that has this like scheduling and access control system called Slurm that is foundational to any work on Frontier. Some of the things that you get some curveballs here. Right? Again, like this is not just a regular everyday Linux system. So back to that Orion Luster file system, the 700 petabyte file system. There are various paths that you can use, and then of course there's also a quota associated with this. And in our particular case, our quota is 150 terabytes, which works well. It's roomy. We don't necessarily have to worry about disk space. When you first log into Frontier, you're randomly assigned a login node. You can access an individual login node directly if you like it, but by default, you're assigned to like a random one at the time of the session. The login node is where you do your dev, your little dry runs, whatever else. Very handily, they closely, almost perfectly resemble the actual compute nodes, those 9,000 compute nodes that make up Frontier. And there's a AMD MI210 Instinct GPU, so you can go through AMD ROCm stuff, PyTorch stuff, whatever it is that you're trying to do. And in our case, we're doing distributed multi-GPU and multi-node training. We developed a kind of abstracted framework to be able to use Hugging Face models pretty much universally. So that uses Hugging Face Accelerate, Microsoft DeepSpeed, HPE Slingshot, libfabric for the multi-node interconnect, an AMD ROCm library called RICL, which is their equivalent to Nickel. And then there is basically a plugin from AWS to be able to use libfabric over the Slingshot multi-node interconnect to make it just kind of look like a generic, NVIDIA multi-node cluster setup. But then you start to realize, oh, there's some quirks here. And as I'm kind of like banging my head up against the wall on a couple of different things, I got like a quote from an unnamed, multi-PhD genius at Oak Ridge, and he just kind of looks at me. He's like, Chris, Chris, he kind of choked up a little too. He said, Chris, I feel you, man. Like, every time we get a new one of these things, you realize quickly it's a snowflake. You've got the system. Nothing like it has ever been built in the history of humanity. So there's a bit of a curve in terms of figuring out where the little demons for that system lie. As part of this, we developed a framework that we're going to be releasing on GitHub called Slurm Docker GPU. It's an environment that essentially mirrors the Frontier Slurm and execution environment, but allows you to do it on any machine that has NVIDIA or AMD GPUs. So you can kind of, you can get all your Slurm stuff lined up, your multi-node stuff, whatever else. It kind of fakes multiple local GPUs. And that helps not only in terms of porting workloads from CUDA to AMD ROCm, but also, kind of getting your multi-node interconnect working so that you can fully utilize I think it's 200 gigabytes a second is the interconnect node speed, something like that, gigabytes, not bits. Then we also developed Frontier Do, which essentially by default, you can provide overrides, but implements like best practice for AI workloads on Frontier. Again, using Hugging Face transformers, Accelerate, DeepSpeed, fully sharded data parallel, or Megatron LM. Classic, step 4, profit, hopefully. So the most important thing is if you've tried to do like big GPU stuff, number one, you can back up a dump truck full of money to NVIDIA, and there'll just be a bigger dump truck with more money in front of you. There's like a 52-week lead time, something like that for GPUs. you have to beg and plead to get them out of AWS or GCP, anything like that. So in this particular case, not only is it free, the GPUs are just there. You say, Slurm, go do this, Frontier, go do this, and poof, something pops out the other side. And then, needless to say, it's free. So, a kind of an equivalent for the 20,000 node hours in GCP or something like that, it'd be roughly $200,000. So that's money that we saved. And that's it. Thank you.
That was amazing, Kristian. Amazing level of detail. Not for discussion right now in the questions, but at one ClueCon, we had a "Where were you conceived?" conversation. And Kristian had the most interesting answer to that. I remember it well. Anyway, we'll deal with that another time. Who's got some questions for Kristian here? Fascinating stuff. Jack's bang on the money there. Well, Jack, I like to reward your keenness. So you jump in, you can warm it up for people.
Okay. So this is so cool. So you could have done this commercially, but the queues are so long, and because you're working with government agencies, you have the back door to get into just a huge data center GPUs.
Yes.
Oh, so cool. Okay. So if I get in there and I have my PyTorch or my TensorFlow Python things, would I be able to swim in this, or is it really just too far askew that I wouldn't ever be able to figure it out?
No, that's exactly what we do. This is all fundamentally PyTorch, and kind of with some of the other like alphabet soup and jargon I threw in here.
Well, I hadn't heard of I do CUDA, but I don't do whatever the other thing was. And so could I learn it? It's all reasonable, right?
It's PyTorch is a fantastic abstraction layer, and AMD, given let's see here, like in AI and data center GPU space, NVIDIA has at least 90% market share. Intel, AMD are kind of single digit, somewhere in there. So the AMD equivalent to CUDA is called ROCm, R-O-C-M.
Okay, I got to learn that.
Yeah, PyTorch mostly handles it. There's some little quirks.
Okay, so last question. Just that data center, can you compare that data center to the data center that OpenAI used to generate GPT-4? Is it apples and apples, or is it apples and watermelons?
So from a compute performance standpoint, big tech, like the federal government has a big budget, but big tech has some cash to throw around as well. So both Frontier and some of these other DOE systems and your OpenAIs and your Microsofts and your Metas or whatever else, they typically start pushing about 100,000 GPUs. That's kind of the current. Frontier is 75,000, so pretty close.
Oh, pretty close, okay.
Yeah.
Okay, thank you.
Sure.
Okay, any more? Oh, there's a question. There's Diego around there. Let's run over. Here we are, Diego.
Very interesting. I like, by the way, the name you gave to the project Fermi. It was an Italian scientist.
I was going to say, great Italian scientist.
Thank you. About this project, so will this be commercial AI models, vertical for the nuclear applications? Will it be some kind of open weight models? How do you envision that?
So, needless to say, I've been using Linux since like 1996 or something like that. Basically, I've lived my entire life in the open source ecosystem. We're standing on the shoulders of a lot of giants here, and we feel that not only for kind of the openness and transparency that is also present in nuclear, that it actually aligns really well with open source. The nuclear industry is basically open source. They don't call it that, but it is. It helps when a lot of these plants are essentially geographic regulated monopolies. They're not exactly fighting with each other. So there's a lot of sharing of information, et cetera. And so we felt that making this an open release was absolutely paramount to the work that we're doing. So the variants of the Fermi family of models will be on Hugging Face under our organization. And our training pipelines, evaluation, benchmarking, et cetera, to basically be able to reproduce our results will be on GitHub. And in our particular case, there are a variety of things that we're doing, like Splade v2, the sparse embeddings approach, was a little challenging because There is not a commercial use compliant licensed version of it available. So, we went back to the paper and implemented our own variant that actually slightly outperforms the original from scratch. And so we're making all of this available under a commercial use capable license on Hugging Face and GitHub.
Thank you. Very interesting.
Amazing. Any more questions for Kristian here? I'm trying my... Oh, yeah, right. Okay, right at the back here. Here we are, sir.
A lot of times there's a tight relationship between business needs and innovation, where sometimes we innovate something and then we decide that we can solve problems that we didn't even know were achievable. And a lot of times business needs just force us to then innovate. How do you kind of see the relationship with that in terms of quantum computing? And, is it kind of like, if you build it, they will come? Or do you think it's more of like, it's coming, so now we need to build it right now? And how does that kind of relate to some of the business projects and applications that you've been working on?
Sure. So interesting mentioning quantum. The other kind of big thing here is, needless to say, when people are buying up hundreds of thousands of GPUs, they consume a lot of power. So there's a lot of interaction between nuclear as a source of clean power, reliable 24/7, 365, to power a lot of data centers and systems and whatever. And they're looking at a lot of the quantum compute research is actually done in conjunction with small modular reactor startups like Oklo, TerraPower, NewScale, and some others. That's probably like the only interaction with quantum I would say that I see throughout the industry. In terms of aligning our work with how it applies to industry, at the end of the day, I'm reading these papers, I'm not writing them. So I'm not a researcher, I'm more of a practitioner. So we approach everything overall with, of course, the key focus of, this is a technology company. At the end of the day, we're in this to make money. And so we kind of keep that in mind when we start really nerding out on some of this stuff. And that was kind of another reason why we really started with a great group of advisors and early users to develop these benchmark frameworks to make sure that all of our blah, blah, blah actually applies really well in practice, in commercial use in the industry. Does that mostly answer your question?
I think John's nodding his head there.
All right.
Thank you, Kristian.